Hello, students of science. In this video, we're going to talk about the different kinds of nuclear radiation. Radiation is basically particles or electromagnetic radiation that is going to be emitted from the nucleus during radioactive decay. So anytime a nucleus is going to be breaking down, trying to get something more simple and stable, you're going to have some sort of radiation released from there. And of course, that can either be energy in the form of a wave, a very high energy wave, or a particle. The energy transferred from radiation can also damage living organisms, so you need different things to sort of shield yourself from the radiation, either the particles or the actual waves that are going to be going through there. And here I'm showing either alpha, beta, or gamma radiation and how those are stopped by different things here. So the way we measure radiation exposure is with a unit called the Roentgen, which we write as capital R. That's the unit used to measure the nuclear radiation exposure. Here you can see on a dial how many Roentgens are being exposed. And this is something that exists on the internet. I don't know why, but Roentgen is my homeboy. A radiation dose is measured in what is called REMS, or Roentgen equivalent in man. Long-term exposure to radiation can cause mutations in DNA, leading of course to an increased risk of cancer, messing up the DNA sequence and all the things in there. You can get exposure to background radiation through anything from cosmic rays to rocks to air to concrete or even radon. This is maybe why a lot of basements that you might see have radon prevention. But yeah, even air, concrete rocks, and even things just shooting down from space all can cause damage to DNA, leading to an increased risk of cancer. This, of course, is the international symbol for radiation. Radiation can be detected by both film badges and Geiger counters. I myself have worn one of these film badges before. You wear it anytime you're around radiation, anything like that, and they pull them out once every couple of weeks or once a month and check to make sure that you're not getting more than you should be getting for your radiation. Geiger counter, of course, is going to be measuring radioactive decay, a little handheld device that can either click or beep depending upon what you are exposing it to or how it's set up. So our three different types of radiation are alpha, beta, and gamma. So let's start with alpha particles. As we mentioned before, that's essentially 2 protons and 2 neutrons. They are slow, they are heavy, and they are the most damaging of our types of radiation. The good news is they can only penetrate about 0.05 millimeters. You could actually stop alpha radiation with a piece of paper or your skin. So as long as they're on the outside of you, they're not going to be causing too much of a problem. Your skin can usually block the biggest damage. Beta particles, well, that's essentially the same thing as an electron. They are not as damaging, but they still can be very harmful if you're getting them in the wrong spots. They can penetrate a little bit more, about 4 millimeters. However, you can stop them with enough wood or tin foil that is thick enough and dense enough to prevent those. And then there's gamma radiation. It's not a particle, but it is a burst of very, very high energy waves. These are the fastest, these are the lightest, but these are also the least damaging. They can go over a meter through a person. You can stop those, but you need large amounts of either lead or concrete. When you're worried about radiation coming off of like a nuclear reactor, the alpha and the beta particles aren't what you really need to worry about. You can stop those very easily. It's the gamma radiation. Even though it's the least damaging, that's not to say it's not damaging. It's the one that can go through all the stuff the easiest, so you need to spend a lot of energy and a lot of time to sort of stop that. A lot of lead and a lot of concrete on the outside of it. So to recap, we've got our alpha, very dangerous, can ionize just about anything it comes in contact with. But remember, not very penetrating. Paper would stop it. Beta, a little bit less damaging, however, it can penetrate through a lot more. It could go through paper, aluminum, however, as in aluminum foil, that would stop it. Then we have gamma. Remember, the least damaging, but the most penetrating. Now, radiation, of course, has lots of different applications aside from giving you cancer. You can use what's called radiometric dating to determine the approximate age of an object by the amount of certain radioactive nuclides that it happens to have. So let's say we have this rock, and it's all uranium at the beginning. It has 0 half-lives because, of course, we're looking at T0. So let's say the rock has just crystallized and you have nothing but uranium in there. Now, if uranium has a half-life of about 1 billion years, 1 billion years later, half of that uranium has decayed into lead. So here we are looking at half of it is going to be lead. At 2 billion years, half of that remaining uranium will have decayed into lead. And at 3 billion years, half of that remaining stuff has decayed as well. So by looking at the ratios of the uranium and the lead, you can figure out, oh hey, this has gone through 2.5 or 3 half-lives. We can see, here's when the rock initially forms, it has some radioactive stuff. At the half-life, half of it is gone, and so on and so forth. By measuring the amount, we can calculate the age of the rock. So here's the parent isotopes, what we started with. Here's the accumulating daughter isotopes. Look at the ratio between those, and that tells you how old the rock is. We can also use radioactive tracers. This is a way that you can image body functions by following radiation in the body. So of course you might inject it in your arm, in a vein, something like that. I myself have had this done with radioactive water. And then you're measuring where in the brain you're actually going to see this scintillation, where it's going to be breaking down. So you inject it in there and trace it throughout the rest of the body. You could also do that in a plant. Inject a radioactive, so this is radio-labeled phosphorus, and then you track and see where in the plant is that radio-labeled phosphorus actually going to. And of course, radiation treatment. Certain types of radiation can be used to destroy cancerous cells. You might hear someone going in for radiation therapy to kill cancer. Well, they're going to be aiming radiation at that particular tumor or at that particular area of cells. Remember, radiation, very damaging. However, we're not talking total body. Now we're just focusing it on the parts of the body that are obviously causing the damage. Even non-biological applications of radioactive tracing can be found. You could put small amounts like a radioactive tracer in the water and then look and see in the ground where is some of that radiation coming through. If you're getting a lot of it coming through in this particular area, you know that you probably have a leak down there. So this would save a lot of time and energy instead of having to dig up the whole pipe. Now you know, hey, this is the one area where I can see those radioactive tracers.